And we are recording. Welcome to the evening of Python coding. This is the meetup that each month we go and check out some Python tool or library. And we always have speakers. Sometimes there are people who develop the tools, and sometimes they're just the community who's interested in doing something very interesting. So tonight is part of our community is going to talk about something. Richard has been coming to this meetup for many times, and I don't know when he started. And you know what? I'll ask Richard to talk what he's going to talk about, and he's going to introduce himself and tell us how long he's been coming to this meetup. Richard.
Oh, I've been coming to the meetup for about a year, pretty much. Yeah. 12 meetings, I guess. So I just joined meetup March last year, something like that.
Yeah. And you've been a regular.
Yeah. So
go ahead, tell us what you're going to demo today, because you something to do with music and machine learning.
Yeah, let me share my screen.
Okay.
Okay. I'm going to be talking about a model called CLAP. Stands for Contrastive Language Audio Pre-Training. And it caught my interest because it embeds sound and text in the same vector space. And that allows you, for instance, to say, give me the sound of a flute amongst my audio files, and it will find it without any labeling of the audio file. They trained this library in about 2.5 million sounds. So I snagged some of their work. And it's fuzzy labeling. Like if you look at some of the sounds they have, like say this one here, big blade big dot wave. The description that goes with it is a person pulling silverware out of the dishwasher. Since those two things are associated with each other, after the training's complete, they will be occupying proximity in the embedded space. You look at some things like, say, I don't see one right now. Eric final, that's pretty non-descriptive to me. Doesn't mean anything. And it is a person tapping on a percussive instrument. I might call that noise in the set. So it's interesting, out of 2.5 million samples, hopefully the noise will go away. So if you see something like a wave file that is a flute and the description is a flute, the signal is going to override the noise. So here's the way they do this. They have two neural networks. One is an audio encoder and one's a text encoder. The audio encoder is a neural network. It takes the wave files, runs a MEL spectrogram, and goes through 12 attention layers. The output of those are a 512 dimensional vector. On the text side, it uses the BERT algorithm, but an improved BERT algorithm. I don't know how you pronounce that. And it's another transformer model. It takes a text string, splits it into tokens, goes through another 12 attention layers, and puts it into a 512D vector. Both of those go into a shared embedding space. So this is their diagram from their white paper. If the sound is less than 10 seconds long, it goes straight into the encoder. If it's more than 10 seconds, it's broken into 10-second chunks before it eventually goes into the encoder. And then the output of the encoder is this 1x512 vector here. On the text side, you notice they prefer sentences, not labels and phrases. So if the WAV file has just a label, they expand it out into a sentence and then go into the text encoder, again into a 512 by 1 space. What I did is wrote a program that loads that model, loads the pre-trained clap model. I load it from Hugging Face. Then I load a folder of audio files off my PC. The program then converts those files into the 512D embedding space, prompts for a query for a text string. Once I get that query, I embed that query into the 5D space. Then I compute the similarity between the WAV files that I brought in and the query. Then I print out a ranking table, and then I visualize it. So in summary, I load the clips, type a query, and rank the results. And the way I rank the results, you may be familiar with the cosine dot product. And basically that is finding similarities between vectors based on their angular direction from each other. So for instance, if there's a flute sound, the text query says pan flute, those might be aligned. Probably not. Oh, the similarity scores between -1 and +1. A perfect match would be +1. And my work, I never found scores much higher than 5/10 or 6/10. If they're completely unrelated, like a piano, and you type a flute, then those are orthogonal, so it'll be around 0. Semantic opposites almost never occurs. I've gotten scores as high as, I don't know, maybe -0.04 or something like that. Now, I also added something that the researchers do. It's not in their paper. You have to squander around to find it, but it's hard for me. I mean, we can't visualize 512 dimensions, right? So I wanted to make a visualization of this, and I used something called PCA, and it's a way to visualize the high dimensions. It's a standard scikit library. And the way it works is it takes my vectors, finds the widest direction of the vectors from the mean. The widest direction becomes the x-axis on my plot. The second most is the y-axis. Now, here's what my plot looks like. So when I read a bunch of WAV files in, you're going to see, like, for instance, in my folder, I have noise, drums, piano, flute, and guitar. If you type flute, then the angular difference between the description of the flute and the flute will be pretty close. And so that'll be the matchup. That's basically how it works. And I made a GitHub repo. I don't know if anybody tried to download that. I worked really hard on making it turnkey so that anybody could load on their system without clobbering their main Python install. The way I did that, all of this is what I went over. You can read it later if you want to. Here's my project structure on the GitHub. I have my main program, and I call the PCA, which does the reduction from 512 to 2D. And then in there, you can point the mouse over near to the WAV file and play it. the project.toml is used. Here's how I made it hopefully transparent. If you don't have UV, install UV. I like UV a lot because it creates a virtual environment on the fly. So you install UV, and then all you have to do, I run mine in documents. So you just change to your documents folder, clone my repo, and it creates a laion-clap explore directory. Change to that, type UV sync, and then when you type UV sync, it reads that TOML file and pulls down all the libraries. It takes about, it's fast, it's under a minute. Then to run the demo, you just type UV run Python and the name of the file. So what it does, I'm going to run the demo now. And before I run the demo, I want to tell you that if you do install it on your machine, the very first time it installs it, it's going to download all the weights from the Hugging Face repo. It'll cache those on your machine. So all the future times you run it, it won't grab those. The weights are about 500 megabytes. And my program defaults that if you just type clapdemo.main, it reads a folder called clips. And then I have a command line parameter that if you want to point it to another folder, you just add it to the end of the script. So you can use a GPU. I tried a GPU, but my program is not doing any training. All the training is already done by clap. So we're just doing inference here. So the GPU did not speed anything up. And it increased the repository's repo size by about 6 gigs. I left off the PyTorch GPU model. So if you download my GitHub, it's just the CPU. So I made a folder. It's got about 9 files: bass guitar, bird, a dog barking, water droplets, electric piano, flute, frog, grand piano, noise, trumpet, and acoustic guitar. So here's the prompt for the query. When I type this, I'm going to type a flute. When I type flute, there's the 2D embedding, but don't pay attention to that right now. Look at the similarity ranking here. On the left, this ranking says the likelihood that my sample of a flute is 0.477. The likelihood that it's a frog is minus 0.059. If I go over here and I'll type flute to see if it's a flute sound. Okay, and it's the flute sound. So now watch this. I'm going to type dog. What did it do? Oh, it thinks the trumpet is a dog. So what happened there? What happened there is it expects phrases, not single words. You saw in that Excel file that I grabbed, they had very long descriptions. So I'm going to type a long description. The sound of a barking dog. But barking dog, it finds it. Now, what I examined the model extensively, so I tried to find out where it works and where it breaks. So if I type electric piano, then it finds the electric piano. So I want you to listen to the grand piano and tell me if you hear a difference. And you see the electric piano over here on far left was a match at 0.32 and the grand piano at 0.314. Can anybody tell me the difference between the two? No? I created those two files myself. The difference is I wanted to test the algorithm, the model. The difference is I took an electric piano and added reverb to it. So if I type grand piano, then the model thinks that a grand piano is in a grand space, a cathedral or something. And in fact, it probably has echo, so it found it, right? And here, when I type grand piano, the similarity is 0.524 and the electric is 377. They're a lot further apart than before. So you may be skeptical that I'm reading the labels on the WAV files. So I made another directory in which I removed the labels and I just numbered the files. It's the same files. They're numbered 1 through 9. I'm going to type frog. I don't know if you remember frog was one of the files. I'll type frog. And file number 6 is 1/2, 56% likelihood that that's a frog. Whatever number 4 is, it's barely likely. So let me type number 6. And it's a frog. Let me type 4 to see how dissimilar it is. A piano. So that's proof to me that the models worked. I was confused when I first wrote the program. I thought, oh, it's just reading my WAV files. So I got a file called dog and I typed dog, so what? But it's really working. So another problem with the program, with the model is, I mean, maybe it's not a problem, but I created, let me check. I think it's, a folder I have called 50 files, 50 sounds. These 50 sounds are in groups of 4 different groups of sounds: flutes, vibraphones, violins, and cowbells. So what I'm demonstrating here is that the model clusters similar things adjacent to each other in this 512D space. I'm going to type cowbell. And here you see all the cowbells are clustered together, vibraphones clustered there, flutes over here. Now, there's another problem. I was disappointed with the model. If you look up here on the far left, the cowbell, look, the difference between each one, 0.478, 0.476, 0.475. In fact, I could come up with all different descriptions of cowbells, and it always picks the same one. So globally, it's very good. Locally, it's a little iffy. It's iffy. It's iffy probably for 2 reasons. It wasn't trained on 50 cowbells. I got these from somewhere else on the web, you know. It wasn't trained on 500 guitars. It was trained on 2.5 million sounds, from everything from, you know, babies crying to jackhammers or whatever. So I'm going to do one final demo, and that is I have 150 sounds. And this one I actually did grab from their repo. Not their repo. They don't have any sounds on their repo. They say copyright restrictions keep them from releasing them. So it took a few days of digging around with their links to their links to their links to their white papers to find these. But this is actually part of one of their data sets. And so you see a lot of things are dated 2008, Citizen Cricket, whatever that is. A fountain, a forest cry. Salons, thunderstorm. So once this loads, I want you guys, somebody to tell me my name to type, and I want to see what it finds. If anybody's interested, otherwise I'll just make up a name. Anybody want any names?
What do you mean name?
Name?
You mean you want the name of a sound?
Yeah, name of a sound, and I want to see in this data set of 150, is there any like your sound?
Tree falling in the forest.
Tree falling in forest. Tree falling in forest. Now I have no idea. Huh?
Does it sound at all? You know, that's the
the classic Zen. The sound of one hand clapping. That's what I should type that one. In fact,
actually we'll try it again later.
I mean, the model is called.
So nothing that's similar, 0.344, and it's something called forest cry. So let me see what it sounds like. Anyway, that's what it found.
Okay, let's try the one hand clapping.
Okay.
Wait a second.
So we couldn't hear that forest crying one at our end. What does it sound like? What was the actual sound coming out?
Oh, you couldn't hear it?
No.
Oh, okay.
It's very short.
Huh?
It's very short. This is why.
No, it was long. I have my speaker turned down. Could you hear any of the sounds?
Yes,
Did
it
I
could,
play?
but they're very short.
Okay. Did you hear
There's
it?
a little, yeah, a little blip. There's like
It
a
sounded like a bird or something. The sound of one hand.
So how do we know it's not just picking up on the file name?
Oh, because I just demonstrated that a while back that when I had the file names, I rewrote the directory and just had them all numbered.
Mhm.
Were you here for that, or did you? Did I go too fast?
No.
Maybe. And on the cowbells, it's called C-bell, right?
Yeah.
And I type cowbell, and the flutes are just called FLU. So it's actually ingesting the WAV file,
Mhm.
doing the spectrogram conversion, running it through the model, and embedding it in the space.
So that spectrogram conversion on the 150 files that you just did there, that was done that quickly?
Yeah.
Or was
They
that
already had converted it.
right?
He only checks the text. The conversion takes like no time. It's a very small model. Roberta is one of the first. It's an enhancement to one of the very first BERT models.
Mhm.
BERT was like one of the first transformers that was around, if not the first one. It was 2018 or 17 they came up with BERT. 2017 they came up with transformers. 2018 was BERT, was one of the most famous ones, and it's actually tiny. It's really tiny compared to today models. It's whoa, minuscule. So Roberta was an enhancement of BERT. Okay, what did you have this time? Kitchen salad.
Oh, that's the sound of one hand clapping to the
Apparently.
similarity of 0.36.
This similarity is 0.36. Is it good to consider?
Oh, that does sound like one hand clapping. Pardon me?
Yeah, the similarity is 0.36, right? So is it good to consider that amount, or it should be about 0.5?
Is it considered the similarity goes from the most similar would be 1.0. So this -1 is completely dissimilar. +1 is completely identical. So they range, you can see what the range is typically on the similarity. In this case, it's like 0.3, 0.2. Where I had musical instruments defined and I knew what they were and I called them. Even then, the similarity was just like 1/2 to 0.6, something like that. Now, I didn't try putting a sine wave in and typing sine wave because it said it wasn't trained on that, so I didn't bother doing it. So that's what clap is all about.
By the way, the 0.5 maybe because it's only looking at only part of the vector that has to do with the text. You remember there's a vector part of the text and then there's the wave part of the text. I assume
Right.
the library, if you take an actual sound and embed it, then it will be able, the vector constructed will be much bigger. Otherwise, if you only look at the text, then the text is only a very small part of the vector.
Yeah, and it's interesting that if you just write a simple label like I did, then they try to expand it into a sentence, really. And I didn't chase that down in their architecture to see how they did that.
It's Roberta. Roberta does this. It's the embedding of whatever Roberta does. But never mind. Guys, any questions to Richard?
I'm curious as to, I think you mentioned that you did try it on the GPU versus the CPU and you didn't see any performance increase. That seems anomalous. I'm curious as to why you think that might be the case.
Well, it's not training. It's just doing inference. So it reads the wave file and uses the model as it exists. So it's not doing any floating point computation per se to do that.
Oh, it does. It's just so tiny.
It's a tiny amount of computation.
So
because these sound files are so small?
It's tiny. What you have here, it's like, first of all, he's only doing the text part. He's only embedding the text part. Correct, Richard?
No, I'm embedding the wave files too.
Yeah, no, but the wave,
small,
maybe
correct?
the wave files are so small, there's no benefit to the GPU.
Well, each time I started the program, that's when it's you know, I have it on an SSD, so it reads the wave files in very quickly, split second to read the wave files. The delay of 10 seconds, 12 seconds is the actual ingestion and embedding into the space using my CPU. And so since it's only like 10 seconds on my CPU, it might have been faster on the GPU, but maybe I didn't spend enough time with it.
So
Like
Richard,
it might have been 5 seconds instead of 10, so I didn't notice and I didn't chase that down. So yeah, it makes sense. It could be somewhat faster. I just didn't
Richard,
explore it a
let
lot.
me help you out here. Let me help you out. GPUs are good when you serialize a lot of data up front and you push it in there. Then they do many parallel computations. So if you have like 100,000 files all already loaded up and the vectors are ready, then you put it in the GPU, then the GPU will give you an advantage. Like when you're doing training of a neural network, then this is what happens. Like all the data is waiting out there already. Also, uploading stuff to the GPU takes time. So basically, if you have a pipeline of things already ready to be uploaded, and then it has an advantage. Otherwise, you're spending just a lot of time just to prepare everything, and then in a split second it does a small computation, and then that's it. So you don't see any benefit. In fact, the fact that you're uploading everything there may take you even more time, because you have to build it up in a specific way that the GPU will understand. So this might be why what's happening. And whatever he's doing here is really tiny. When you usually use GPUs for huge workloads. So
these are small. These are very small samples that are being classified.
All the ones I did on purpose, I made them like around 8 seconds. A few of them are maybe 12 or 20 seconds.
Yeah, but even if they were the longer one, you would take them chunk them into 10 seconds pieces and then compress them, correct?
Yeah, and they're doing them one at a time too. They're not blasting all. They're not blasting all 9 of them in parallel, or all 50 of them in parallel.
And all of those are happening in the CPU before you actually hit the GPU. So, guys, this is like an example where if you had like 100,000 of them, then yeah. But
see, I didn't try that. I could have taken their 250,000 data set and tried it, but I didn't. I had the GPU loaded. I have a 4060, so I don't have a super powerful GPU. The basic entry level.
Any more questions? Questions going once?
And I had one other thing I wanted to put. The number of coefficients or weights in this model is about 195 million. I looked at the internals of their model. I thought that was interesting, that it was so high.
0.1 billion, this is what you're saying? Or no?
195 billion, yeah.
So 0.1 billion, it's a tiny model compared to today's models.
Well, yeah. I mean, compared to what we're doing on the web, yes, it's tiny.
Okay, so even the GPU will not even be fully loaded, like unless it's a very old GPU. So,
right. Well, that's a good point.
Philip, you have a question? Jump in.
Yeah, I do. Thank you. First of all, thanks, Richard, for taking us through this. My question is, what got you interested in this application of machine learning? Do you generally work with audio files, or do you kind of have a musical background? If you maybe just touch on that. Thank you.
Oh, I do. I'm a musician. I have a musical background. I've been a hardware designer. Traditionally, I've designed synthesizers and music chips, but lately I switched over to the software world. And Jacob asked me if I could do a demo, and he says, since you're a musician, why don't you pick something in music? So I went through the Python library, and I'm just scrolling through the Python audio library, and this one caught my attention. And that's what made me do it in preparation for this. I wasn't doing this particular thing before.
Right. Okay.
Yeah. However, I have worked in the past few weeks writing Python scripts to generate music by analyzing pre-existing music and making something similar to that and loading it into my DAW. And some of the results are interesting, some are creepy, and some are just horrible. But it's working. I've got it working.
That sounds pretty cool.
It's just a lifelong interest in audio. It basically started in 8th grade, where I was repairing guitar amplifiers for the kids that were in bands. That's how I got started years ago.
Cool. That's incredible. Thank you.
Yeah.
Any other questions by anyone? Questions going once? Questions going twice. Last time for questions. Questions going 3 times. Well, at this point, since there are no more questions, I would like to make some noise and thank you, Richard, for this very nice demo. And you can put in all sorts of stuff on the screen.
Oh, cool. I'm glad you guys, I hope you guys got something out of it. I hope it didn't lose you.
No, it is very interesting. We loved it. Thank you. Don't go away. Don't go away. We're not done yet. I'm just stopping the formal recording. So I'm stopping it now.